Let's discuss finding equivalent resistance. This is sort of like adding up resistors, but it's not always so simple. Today we're going to discuss three cases. The first case that we're going to discuss is the series circuit. A series circuit looks something like this, and our equation for the series circuit reads that the equivalent resistance, which we call Req, is equal to R1 plus R2 plus yada yada yada, and all we do is really just add up these resistors all the way up to however many resistors we have. Here, as you can see, we have three resistors, so our equivalent resistance, Req, is going to be 10 ohms plus 20 ohms plus 55 ohms. So our equivalent resistance in this case ends up being 85 ohms. And that's sort of the resistance that's felt overall in this circuit by this current provided by this potential here. So that is our series circuit, pure series. The next type of circuit we could have is a parallel circuit. For the parallel circuit, our equation is going to be a little bit different. So for this parallel circuit, the equation reads 1 over the equivalent resistance, so the inverse of that is equal to 1 over the first resistance plus 1 over the second resistance plus ... all the way out to 1 over the nth resistance. So here you can see we have 1, 2, 3, 4 resistors in parallel. And again, what that means by them being in parallel is they share a starting node here and they share an ending node here. So these are in parallel, and what we're going to do for this to find the equivalent resistance is to say 1 over Req equals 1 over 10, that's our first resistor, plus 1 over 20 plus 1 over 25 plus 1 over 100. And what I'm going to do here, remember to add fractions, we need to have a common denominator, and the least common denominator here is 100. So 1 out of 10 turns into 10 out of 100. 1 out of 20 turns into 5 out of 100. 1 out of 25 turns into 4 out of 100. And we can keep 1 out of 100 the same. And again, when we add fractions, we just add across the top and we keep that denominator the same. So 10 plus 5 plus 4 plus 1 gives me 20 over 100. So we have a couple of final steps. What we're going to do next is cross multiply. So we get 100 times 1 is 100 equals 20 times Req. And our final step for finding the equivalent resistance is to divide by this 20 on both sides. I can cancel it out here, and I find out that my equivalent resistance, Req, is 5 ohms. So even though we had all of those big resistors up here, all they really add up to in this circuit is just 5 ohms. The next case that we'll consider, we're going to do a sort of complex mixed circuit. Again, our rule of thumb is to work from the inside out. In this circuit, my innermost thing is here. So we have R4 and R5. R4 and R5 are in parallel. So again, for parallel, we're going to say 1 over R4, 5 equals 1 over 3 plus 1 over 6. Our common denominator for these fractions, again this is R4, 5, is going to be 6. So 1 out of 3 turns into 2 out of 6, and we can leave 1/6 alone. We add the numerators of these fractions, so 1 over R4, 5 is equal to 3 over 6. We cross multiply, we get 6 equals 3 times R4, 5, and for our last step we're dividing by 3. These 3's cancel out, and I get R4, 5 equals 2 ohms. So what I'm going to do with these is, as always, just redraw the circuit to show how I've simplified it. So I'm going to quickly redraw this. So now that I've redrawn this, what we did, we left R3 the same, that was 100. We left R2 the same, that was 23. And we turned our resistors 4 and 5, which were in parallel, into R4, 5. And their equivalent resistance was 2 ohms. Down here I still have R6, which is 5 ohms, and then R1, which is 10 ohms. So the next thing I'm going to do, again working from the inside out, is I have these two, R2 and R4, 5, which are in series. And so what I'm going to do with these, because they're in series, I can just add them up. So R2, 4, 5, which is what I'm going to call their sort of mini equivalent resistance, is equal to 2 ohms plus 23 ohms. So for R2, 4, 5, I get 10 ohms. So I'm going to draw my simplified circuit again. And for my simplified circuit, what I did was I turned R2 and R4, 5 into one resistor, with which I called R2, 4, 5, and those had an equivalent resistance of 25 ohms. R3 stayed the same at 100, R5 stayed the same at 5, and R1 stayed the same at 10. So the next thing I'm going to deal with is going to be these two equivalent resistances and resistor in parallel. So for the ones in parallel, which I labeled P, I'm going to do 1 over R2, 3, 4, 5. I know my numbers are getting a little scrunched up, equals 1 over 25 plus 1 over 100. The common denominator for these two fractions, when I'm going to be adding these up, is going to be 100. So 1 over 25 turns into 4 over 100. I leave 1 over 100 the same. I add the numerators of these fractions, so I get R2, 3, 4, 5 equals 5 over 100. I cross multiply. 100 times 1 is 100. It's equal to 5 times R2, 3, 4, 5. And I divide by 5 here on both sides. This cancels out, and I get R2, 3, 4, 5 is equal to 20 ohms. So I'm almost at the end of my journey here. I'm going to redraw my circuit one more time, even more simplified. So now at the top here, I have this equivalent resistance R2, 3, 4, 5, lots of numbers here, equals 20. This is sort of how I keep track of what I've already added up by sort of scrunching in all these numbers into the subscript for the resistance. So R2, 3, 4, 5 is 20 ohms, R5 is still 5 ohms, and is still 5 ohms, and R1 is still 10 ohms. And now finally, I just have a simple series circuit. And so for my series circuit, I just add up these, and this is going to be REQ. This is I'm on my way to my final answer. It's just going to be 20 plus 5 plus 10. I add up resistors that are in series, and so for my equivalent resistance for this whole messy circuit is 35 ohms. So again, what I did is work from the inside out.